that was all just to clean up what we had last time. Now let's carry on to the new topic, which is heap overflows. So I got some slides, although pretty soon we'll just be into demos anyway. All right. There, that should do it. Any link to learn the basics of heap? Well, I would start with this chapter. We're going to do very simple things on the heap. You'll be, I always make everything very simple. You'll see. So let's talk about what the heap is. Just a question. So you can see the memory map. If you use info-proc map or mappings, it shows you the memory map of a process. And every program has a whole group of memory regions allocated for its use. It has a stack, it might have some heaps and other segments. If you're writing a program in C, you use malloc to allocate space on the heap, and then free to free up the space on the heap. Now, normally, that's the whole point of it. You have something big you want to store, and you want to use it, and then you know when you're done with it, then you free it, then you can reuse that memory later. This is where you can make a program that doesn't use a lot of memory. And if you keep on allocating space and you forget to free it, then you have a program with a memory leak that keeps using up more and more and more memory until it crashes, and that's a very common problem. That was true of Windows 95. If the book is often unnecessarily complicated. My lectures are a simplified version of the book. Anyway, so here's a program, info-proc map. So you see it has a stack, it has some libraries, more libraries, and here it has the heap. So it just has a region of memory set aside for this temporary storage by the heap, and a region set aside for the stack and other range. So here's how the heap works, which, by the way, doesn't matter too much to us for what we're doing in the immediate project, but it matters for the next project. Here's the way the heap is. You assign some data, you tell it how big it is, and it just reserves that much room, and then it has some metadata, the size of the previous chunk in this chunk, the pointer to the next chunk, and the pointer to the previous chunk. The heap is what's called a doubly linked list. You can hop down the chunks, forward, hop, 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 from chunk to chunk, and then you can hop back as chunk, chunk, chunk. It is just a data structure. And by the way, Cisco routers have a routine called check heaps that every few seconds does this. It walks through the heap. It just starts and tries to walk to the end and come back. And if it detects that it can't get back to where it started, then it knows somebody has been corrupting the heap, and then it just throws everything away and reboots the router, which is a really brutal but simple way to deal with exploits and flaws. The normal operating systems will not do that, but in fact, when we get to Windows, you'll see they do have a lot of checks to see if people are trying to exploit your heap. Now, the same thing can go wrong on the heap that goes wrong on the stack. You might have reserve enough data for 50 bytes, and then I write 100 bytes, where there is only room for 50. So it will, just like on the stack, C will stupidly let you do that. So then you will fill up this data, and then you will alter these pointers here, which you're not supposed to be able to alter, and that's what a heap exploit is. But we're going to do a much simpler heap exploit here. So here's the simple heap exploit in the next project. You create a data structure. Here's a structure that has a name, 64 bytes long. Here's a pointer that points to a function. That's where we're carefully making a program that is ridiculously easy to exploit. And then we have a program called a method called winner and a method called no winner. And that's it. Then there's a main function, and what it's going to do is allocate structure on the heap for the data and then the pointer, and then it's going to set this pointer to no winner, and then it's going to run that function, FFP. So the point is, it's going to copy into the name the second argument. So you will be able to override the data here and change that pointer, and then change the address of this function. So this is a carefully designed heap structure that has a pointer that's used to control the instruction pointer. So in this particular case, we will actually be able to control the instruction pointer directly from the heap, which is not normally the situation. And that's ED 205. So let's take a look at that. I've got it here. If I do, all right. So here's the program, 205.c. So up here, it defines a data structure. These are global, a name and a pointer. And there's winner and there's no winner. And Here's where you allocate room for the data and allocate room for the pointer, and assign the pointer to point to the no-winner function, copy the command line argument into the name, and then execute whatever that pointer now points to. So it's pretty simple. So we can run this. Let's try running the program, ed205. It needs two values like AAAA and BBBB. Oh, only one string in this one. Okay, AAA then. Right. Okay, so it works. And you see it tells you here the data is at 8B1A0 and the pointer is at B1F0. So it's further down. So you start at B1A0 and 64 bytes along, you get to B1F0, which is where the next thing is. So if I write more than 64 characters, I'll start overwriting the FP. Okay, so I put it in debugger, ed205, and then I run it with the command AAAA. And now let's look at the registers. Okay, I'm going to have to put a breakpoint in it. Let me check my instructions. I'm going to make it crash. That's one way to do it, but I'd rather control. Let's see if I can do the source code. List 130. I can do the source code. Good. So let's go down here. All right. So I would like to put a breakpoint. I think I need to see more. Let's list 20 to 45. I gotta have a comma. All right, there we are. So this is the string copy that's going to overflow the heap. So I want to do a break before and a break after. So break at 32 and break at 33. All right, now I'm going to run with just 4 A's. Okay, now it has broke before the copy. So if I examine D, there's D. And I can also look at my memory. If I do info proc map mappings, I'll see the memory regions. Here's the stack, and here's the heap. So the heap is at this address. Let's take a look at some of the memory at that address. I just do X, say 150X at that address. All right, it's all full of zeros. Then there's a 51, a 191. There's a little bit of data in there. And down here is an actual address to a code segment. 0804 is where the code usually is. That's pretty good. Now I'm going to continue because it did not do the copy of my A's in there yet. So let's continue. And now look at the heap again. And now here's the A's I put in, 41, 41, 41, 41. And if I keep looking below that, see here's the A's, and down here is the address. So I just need to write enough to fill down there, and I'll change the address. So let me go back to my slides and see if I saved myself. Yep, I did. This is what I used to exploit. Okay, so let's take a look at these exploit files, H1 and H2. So I wrote a file to do it. If I cat H1, there. So here it is in Python 3, import sys. This writes 90 A's. And that's probably enough to fill it. So let's try that, H1. Go back into GDB and list 20 to 40. And I want to put a breakpoint in before and after this, so 32 and 33. B space 33, all right? Then I want to run with the data coming from H1. Okay, now I do info proc mapping to find out where the heap is. And I'll just copy that. And now I examine the data where the heap is. All right. And so here's the address. And there's nothing up here yet. If I do continue to the next breakpoint, it's going to copy that 90 byte thing in. Yeah. And now I examine this memory again. Now, here's the 41, 41, 41 stuff. And it goes right down here and stomps over it. Notice this 617. If I go back up here, here's the 617. So the byte above 617 is the pointer, and it's been trashed, turned into 4141. So 90 is enough to clobber that pointer. And of course, if I continue, it's going to crash with 4141, 4141 in the instruction pointer. So now I know 90 is enough to cause a denial of service. So the next one is just to take 70 A's and then put in 2 zeros, 1s, 2 ups, and 9s. This is still a total of 90 bytes. Remember, I've said before, you always keep the total length of it the same once you find a crash, so you don't drive yourself insane. You want to keep hitting the same flaw in the program with different input to see what's happening. So I know now I've just changed the second part into a pattern that I can understand. So when I run that one, I can just run and let it crash now. I don't really need to examine the heap. Now I understand what's going on. In fact, if I run the previous one, which is $H1, it'll crash at 4141. See, now I can cut through all the nonsense. This is the instruction pointer, and that's some of the A's I put in. So if I run it with H2 and say yes, it crashes with 35, 35, 36, 36. And I filled in numbers. That 35 is 5, 36 is 6. So those 4 bytes ended up in the instruction pointer. So now I know it's 70 plus 1, 2, 3, 4, 5. It's 80 bytes. And the next 4 bytes go in the instruction pointer. So I can improve my exploit again with H3. I write 80 bytes, and then I write 1, 2, 3, 4. And I didn't bother to put in the rest to keep the length the same, although it probably would have been a little more desirable to do that, but I didn't. But if this works, it'll put 1, 2, 3, 4 in the instruction pointer. And so if I run that one, H3, it does put 1, 2, 3, 4 in the instruction pointer. 31 is ASCII for 1 and 32 is ASCII for 2. So now I can put any address I want in there, and I know where to put it. I just need to find out what address to put in there, and I can do that by disassembling winner. This is the function I want to run, so I want to put in that address, 080484CB. I'm going to put it in the clipboard and leave. And I think it's already here as H4. Yeah, there it is, 080484CB. That's it, 080484CB. So it has 80 bytes, and then it makes those the next 4 bytes. So if you run that program, I could do it in the debugger or out of the debugger. Let's just do it in the debugger. I'm already doing it that way. And, oh, it's H4. That's why. There is no H5. Let's try H4. There we go. Now I get the message level passed, which is the winning message. I think I got this from a CTF, easy CTF or something. Anyway, that's the point. That's a simple heap overflow, a very contrived one. So let's go back to the slides and talk about a little more of the theory about this. That's a simple heap overflow. All right. So now when you want to exploit the heap, there is a problem that makes it a little bit harder than the stack. The stack, remember, contains your data, and then it contains the return pointer that it's going to use to return. So a pointer is right there, which goes right in the instruction pointer. Now here, we carefully wrote a program that put a pointer there to make that true on the heap, but normally that is not true on the heap. Normally you're just storing data on the heap, and it doesn't include pointers that go directly into the instruction pointer. So it's a little trickier to exploit. But it does have addresses that are used for writes, in the process I was talking about earlier. So here, suppose I have a series of objects on the heap. They've got data, and they got forward pointers and return pointers. Now when I free this one in the middle, I make this memory available. It has to update this pointer to point to the next one, and this backward pointer to point to that one. So when it does that, it has to write to an address here, and the point is, if I was able to overflow one of these and change these pointers, there's going to be a write operation that I control. I control where it writes, and I control what data is written there. And that means I can do the same thing we did with the format string vulnerability. Remember, that's all it was. The format string gave us the ability with a %n to write to memory, and we were able to control the address it wrote to and the data that was written there. And now we have the same situation. If we can overflow a chunk on the heap, and then that chunk is freed, then we gain the ability to control a write operation. All right, so now, since you can write somewhere, you just need to write somewhere that will eventually end up in the instruction pointer. And here we have the same thing we've done before. You can hit the global offset table like we did before to take over hijack a C function like exit. You can hit the destructors table or these other things we talked about before. There's a bunch of places where addresses are stored that eventually end up in the instruction pointer. Add exit, any function pointer, and so on. So that's the game. Heap Overflow gives you a write operation you control, and sometimes, if you're lucky, it gives you something else you can exploit because you can overflow one chunk of data and hit the next data, and maybe that next data is something valuable to you. So let's take a look at a Kahoot. All right, there it is, 127, Chapter 5. There we go. And I will check the settings, which were somehow wrong last time. Now they're right. Wait a minute now. I see randomized answers, but what about project to the student? Show. That's good. Okay, this is good. All right. So classic mode would be fine. Okay, it's working. All right, I'll give it a few more seconds. That might be all I got. A few more coming in. All right. I'll copy these names for the videos then. I'll give you a few more seconds. There. All right. I think that's good enough. Let's take a look at them. All right. So how do you reserve space on the stack? Good, everybody knows that. You just declare a variable, and by default, it'll put it in the stack local to that routine. Okay? All right. What GDB command shows you where the heap is? That's it. Info-proc mapping shows you the memory map, all the memory segments that are reserved for this process, including the heap. All right, how do you make a new chunk on the heap? That's it. This is how you put it on the stack, and that's how you put it on the heap. All right? All right. Switch command moves EIP to an attacker-controlled value when the stack overflows. That's when you return from a function, it takes the stored return pointer and goes back, and that's when you get control of the box in a Stack Overflow. That's when a number that you've been able to manipulate gets loaded into the EIP, when you return at the end of a function. Okay, which command becomes an arbitrary write after a heap overflow? That's free. When you free a chunk, it will write something, and that turns out to be under your control. All right. Not very many people got that, but we'll see it live in a few minutes here. All right. All right. Which command allows direct control of the EIP after a heap overflow? Again, not a popular answer. That's the one you can't do. The EIP is not on the heap. Even if you overflow all of it, probably none of that directly goes into the EIP. All right. Well, that's why you got to demonstrate it. The heap is a little screwy at first. It's not that hard to use, but it's a little funny. All right. CCAP. And Keegan. Okay. And Hema L, okay? All right. All right, well, it's almost 7, so let's take a 10-minute break. I'll stop the video.